Hello everyone. For this tutorial video, I like to review what the moment of inertia is, as well as give a comprehensive proof of the formula for the moment of inertia, exactly like what I did for torque and angular acceleration in the last video. The moment of inertia is an object's tendency to resist changes in its rotation. And just like with torque, the name may seem very awkward or strange at first, but also comes from Latin, where moment is short for momentum, meaning the motion, movement, or moving power of something. So a moment of inertia can be thought of as literally the moving power, or how much power is needed to rotate the object, or stop it once it is rotating. By Newton's second law, we know that force equals mass times acceleration, i.e. that a more massive object requires more force to accelerate at the same rate. And we remember from the last video that we proved that tangential acceleration or linear acceleration along the circumference of rotation equals the radius of rotation times the angular acceleration. Therefore, we can substitute this in and we get force equals mass times radius times angular acceleration. And we can next multiply both sides by radius to get torque on the left hand side. And the sine factor here would not be necessary, as we are assuming the rotation force is 100% perpendicular. So our formula now becomes torque equals mr squared times angular acceleration. And since we know torque is the rotational version of force and angular acceleration is the rotational version of acceleration, we can deduce that mr squared is the measurement of the rotational mass. And this is more often shorthanded to capital I for inertia. This means that the moment of inertia is a complex sum of all of the particles acting on a solid object, relative to the center of rotation. This means that for something that is solid all the way through, like a rubber ball, stop rotating more easily than something like a ring. And it is also true that objects with a greater sum of individual masses, i.e. more mass overall, are harder to stop and start rotating. Although this is generally a more easily observable fact than the former fact mentioned, i.e. that rotational inertia depends on the distribution of mass as well as the overall mass. I can demonstrate this with a mostly empty box of Pop-Tarts, where the mass is mostly concentrated at the bottom. If I rotate it like this, it will be harder to rotate than if I rotate it like this, where I rotate it at the place where the mass is distributed more. If you have ever worked with a heavy hammer before, like a sledgehammer, you would also notice this is true, as the large end is much more massive than the handle. So if you rotate it at the very end, it is much harder to rotate than if you rotate it at the point along the handle that is directly next to the head. Starting with the next tutorial video, I will begin describing factors that affect an object's motion as accurately as possible, instead of the more general concepts I've been discussing so far, starting with how the density of the materials will affect an object's weight, as well as its resistance to rotation. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.